Another example of the exponential functions. Let's give an equation that models the scenario where we have $5,000 in an investment account right now that we expect to earn 4.9%. So ignoring inflation, or maybe that's already considering inflation, but we're going to gain 4.9% on this account. After our yearly expenses, we're going to donate 3,250 every year towards the account. And this is typically what you would do, right? You're not going to put money into an account and just leave it there and let the interest hit it year after year. Usually, you're going to donate to your retirement account every year or every month. So the equation that we're going to use to model this, the value of the account as a function of time will be the initial value plus a reoccurring investment times time times e to the rt, where t's time. Right, so this really gives you a straight line. Imagine if your interest wasn't there, then this is just whatever your initial value is plus your recurrent investment, and then again the next year, and then again the next year. But then when I multiply it by this exponential function, it takes these values and curves them upward. So let's fill in all the gaps. Our initial amount is $5,000. Oops. $5,000 there, plus our reoccurring amount is 3,250. And we're going to do that every year. So we multiply it by t. And this quantity is being multiplied by e to the r. We're expecting a return of 4.9%. So that's 0.049 times t. So now this is a function that depends on t. And in fact, I think that's answering that first part. Let's jump down here. How much money are we going to have in 20 years? So what's going to be the value when time is equal to 20? And let's go through this slowly. If I take 5,000 and I add 20 times 3,250, that gives me 70,000. If I take 0.049 and I multiply by 20, I get 0.98. All right, e to the 0.98 returns 2.665. And we multiply our value 70,000 by 2.665, we get 186,511 and some change. Okay, so put in money into an account, and if you continue to put money into that account, it's going to grow. And the earlier you can make that account big, the longer it has to grow, right? That's the big idea behind exponential functions. Time is super important. The longer you let things sit and earn value, the faster they get, right? It increases kind of slowly over here, but then over here, it increases pretty sharply. All right, let's answer the second part. If we want 3 million in our account in 20 years, what does our initial investment need to be? So let's copy down that equation again that models our situation. All right, and now we know that we want 3 million over here. We know we still start out with 5,000, but this time our recurring investment is unknown, right? We still want time to be 20 years. Okay, so we can take this relationship and figure out what R has to be. So if we do this, let's figure out what this is first. In fact, I think we already know that. Yeah, we did that over here. right? E to the 0.049 times 20 gave us 2.665. All right, solving for this R value, let's divide 2.665 over to the other side. Let's subtract 5,000. In fact, let's go ahead and figure out what this is. 3,000 divided by 2.66, or sorry, 3 million divided by 2.665 gives you, 112,5703.56 roughly. All right, now let's subtract 5,000 from both sides. We get 112,0703.56 is equal to 20R, and dividing both sides by 20, we find that R is approximately approximately equal to $56,035 and some change. Okay, so if you want $3 million in 20 years, that's probably unrealistic, right? You can't put $56,000 towards your account every single year. So you got a couple different options. You could try to change that 3 million. Maybe you could get away with 2.5 million in retirement. Or if you start earlier, instead of 20 years, you can maybe invest over 40 years, and it'll be a lot easier to hit that 3 million. You probably won't have to invest 56 at all, probably nothing close to it.